Let's now discuss triple integrals in a different coordinate system. Normally, or what we've learned about triple integrals already, is how to calculate the triple integral in our standard rectangular coordinates, right? We have the coordinate axes x, y, and z. And then how we indicate where a point is in space is by we take however many units we marched in the x direction, in the y direction, and in the z direction, right? And this gives us a representation for where we're at in space, and we call these rectangular coordinates. And now we want to introduce so-called cylindrical coordinates. And cylindrical coordinates are not so foreign to us because we're very comfortable with polar coordinates by this point. And informally or intuitively, cylindrical coordinates are polar coordinates plus z, basically. So what we're looking at is we have in the r theta plane, down here somewhere, that's not a very good line, down in the r theta plane, right? Well, that line's no better. We have some distance r from the origin to a point in the r theta plane, and this is at some angle from the positive x-axis, right? These are our polar coordinates, and now we indicate where we're at in cylindrical coordinates by taking r theta z. And so here we're not changing z at all from rectangular coordinates. It's going to be the same. But in cylindrical coordinates, we're looking at kind of polar coordinates in the xy plane, and then our height is still z. So here, this is some height, z. And so we have some conversion formulas, right? So let's go from rectangular to cylindrical. Here. Well, if you remember from polar coordinates, we have that x squared plus y squared equals r squared. And then we have tangent of theta equals y over x. Hopefully we're familiar with these. And then we also have that z equals z. And so for the conversion from rectangular to cylindrical and vice versa, you'll notice that z is unchanged. And so really we are just thinking about, well, instead of xy coordinates, let's think about polar coordinates instead for those two variables. And we have, kind of get this out of the way here, we also have conversion from cylindrical to rectangular. And this is x is r cosine theta, y is r sine theta, and z is, again, just z. And so we can use these sets of equations here, these conversion formulas, to go interchangeably between rectangular and cylindrical coordinates. And now what we want to think about here is defining the triple integral, but now in cylindrical coordinates. And so when we're trying to define, so here's what we want. We want the triple integral over some cylindrical box, we'll call it B, over some cylindrical box B of f of r theta z dv. We want a definition for this triple integral. And this is probably something that hopefully by now you guys are used to how the construction goes, right? How does a construction go? How has it always gone? Well, it's different flavors of the same idea here. And it's you take whatever shape we're looking at here. So here we're looking at a cylindrical box, which will look like a 3D trapezoid with kind of some curved, like the long and short ends are curved here, right? And what do we do? So we have R is going to be in the interval AB. Theta is going to be between two theta values, alpha and beta. And then we also have now Z is between two values like C and D, right? This describes our rectangular box here. And so B is the set of triples R theta Z such that, well, R is between A and B, theta is between alpha and beta, and and Z is between C and D, right? And so this is how we're describing the box B. And how have we defined the integral in the past? Well, we introduce a partition, right? And so here, this in red, this is R going from A to B, and we can introduce a partition into like subradii, right? And I can do kind of the same thing up here so you can get an idea of what's going on. And then we also have, well, we're starting at some theta equals alpha, and we end at some theta equals beta. We can also partition this interval. And so let's say we partition A, B into L subintervals. Okay, and then so we can partition our theta interval as well and get these kind of slices like this, right? And then let's say we partition alpha beta into M subintervals. Okay, and then lastly, we can kind of partition Z, the Z interval, right? And so maybe I'll write it up here. We partition CD into N subintervals. Okay, and so you can kind of picture at each Z level, kind of we get this grid-like thing that we're seeing at the bottom and the top here. And then from this partition, we can define these smaller cubes or these smaller cylindrical box regions, right? And so let's take a look at what one of these boxes looks like. We'll go on to the next page here. And so again, you know, it looks something like this, except now we're looking at the mini ones, right? And so this will be like, let's say this is BIJK, where I is partitioning, or I is the index for the partitions of AB. And so here, you know, what is this distance down here, this change in radius? Well, this is the interval Ri minus 1 to Ri, right? That's for the change in radius with a length. The length here would be delta R. Then we need the length of this edge here, right? And this edge here is going to be, if you remember, this is R. So first off, this is the interval theta j minus 1 to theta j, right? These are partitions of our angles. And so the length here, then, so the length of this is, if you'll recall a formula for arc length, like of just part of a circle spanned out by an angle theta, is r times theta. And so here this arc length curve is going to be r, our radius, times delta theta, right? And then lastly, we need the height of this box. And the height of this box is, well, so this is the interval zk minus 1 to zk, right? This is some partition, some subinterval along the z-axis here. Well, then its length is going to be delta z. And so we can get an approximation for, or we get a formula for the volume of this bijk here, which is, again, remember, not the entire thing, but one of these sub boxes on the interior here. Well, then this is going to be delta r times r delta theta times delta z, which is going to be r delta theta delta z, right? And so next, we need a formula for approximate volume between, so remember, this is the function w equals f of r theta z. And so to understand what volume we're trying to calculate, we need a fourth spatial dimension, or we need to be able to picture a fourth spatial dimension, which we can't do, right? And so I'll just kind of draw it over here. You can imagine in some fourth spatial dimension, we can observe how the function is behaving over this cylindrical box, right, in some way. It's doing something. And then we want kind of the volume of the four-dimensional solid, right? This is what we want. And how do we calculate the volume of this four-dimensional solid? Well, we take the volume of this box, which is our base, right? This cylindrical box B is the base of this four-dimensional solid. And then we need to take that times the height. And the height is going to be given by picking a test point or a sample point here in each bijk. And the sample points we'll call r of ijk star theta ijk star and z ijk star. This is a point that we're going to see if we evaluate the function at that point. Maybe if I use yellow here, you know, if we pick some sample point, this rijk star theta ijk star, and then z ijk star, well, then this height here that will give us the volume, or an approximation of the volume of the solid over this mini ijk box here, right? This height is given by f of the sample point, right? And so that means we can approximate this four-dimensional, or the volume of this four-dimensional solid by taking the triple sum, where I runs from 1 to L, J runs from 1 to M, and k runs from 1 to n of, well, the height, which is f of our sample point, z, I, j, k star, and then times this delta v here, right? Because remember, the volume of this four-dimensional solid is going to be the volume, the three-dimensional volume of the base times the height. And as we've seen before, you can pass from approximation to an exact value by taking the limit here. And so we have that v is precisely the limit as L, M, and N all tend to infinity of this triple sum. I runs from 1 to L, J runs from 1 to M, K goes from 1 to N of F. So F of our sample point, Rijk star, theta ijk star, Zijk star, and then delta V. And now we can introduce a definition. So this will be a definition. This volume is what we're calling the triple integral over this rectangular box, or this cylindrical box B, of f of r theta z dv. Okay, and now we have Fubini's theorem once again for this triple integral, which is that the triple integral over this cylindrical box B, where f is a function of r, theta, and z dv, well, this is the iterated integral, and we'll say r goes from a to b, theta goes from alpha to beta, and z goes from c to d of, well, then we have f of r, theta, z. And now what is dv, right? dv came from taking the limit of delta v, and delta v was r, delta theta, delta z. And so that means dv is now r, dr, d theta, dz. And so just like when we were defining double integrals in polar coordinates, we now pick up this r, right? And so dv, which is equal to dx, dy, dz, is equal to r, dr, d theta, dz. Okay, and so when you're setting up an integral in cylindrical coordinates, you cannot forget this extra r. Like, you can't just translate the differentials right away. You also have to multiply by r here. And once again, by Fubini, we have that you can integrate these in any order you want. And so we have 6 possible orders of integration. We have dr, d theta, dz, which is shown up here. We also have dr, dz, d theta. We have d theta, dr, dz, d theta, dz, dr. And then we have dz, dr, d theta, and dz, d theta, dr. And so you can set up your integral in whichever of these is the most convenient for a given scenario. So now I'd like to finish the video off with a few examples. One is just a standard example so we can see what triple integral in cylindrical coordinates looks like. And then the others will be over like generalized regions. And so actually, I think what I'm going to do is, let's split this into 2 smaller videos. Let's leave this as the lecture portion. And then in the next video, I will go over all 3 examples. So this video can be a lecture portion, and then the next video will be an examples portion. And then we'll do something analogous for spherical coordinates as well.